FIR filter design using a time window. When designing a filter, it's theoretically sufficient to just take the inverse Fourier transform of the desired frequency response and use the impulse response values as filter coefficients. However, this method works, but in many cases the desired frequency response is zero in the stopband and there is no defined transition region. This frequency response with finite length, for example a pulse, leads to an impulse response with unlimited length, for example sync, which is not possible in practice. As a result, in practice, we approximate the desired frequency response by its truncation. The effect of shortening the impulse response to the length of n samples is like multiplying it with a window function of width n. That's the idea. The effect of the multiplication in time window is equivalent to the convolution of the desired frequency response with the Fourier transform of the window function in the frequency domain, which is expressed as follows. H practical of n is equal to H desired of n or H ideal of n times W of n window, time window. So, H practical of e to the power of j omega will be equal to 1 over 2 pi integration from minus pi up to pi H desired of e to the power of j theta times W of e to the power of j omega minus theta d theta, convolution in frequency domain. And it's of course a continuous, so we need to have integration, where H desired of n, W of n, and H practical of n are ideal impulse response, time window, and practical impulse response, respectively. The basis of such a method is to choose a suitable window function that changes the desired transfer function so that the resulting answer is as close to the desired answer as possible. Each window function is a compromise between the width of the main lobe and the levels of the side lobes. Now, the convolution of the Fourier transform of the window function and the desired transfer function has two important effects. The first one. The first effect is that the transition region will now have a finite length, which is approximately equal to the width of the main lobe of the Fourier transform of the window function. The second effect is that the response will now have a leakage from the stopband into the passband, which leads to a non-zero attenuation in the stopband. The level of stopband attenuation will depend on the levels of the side lobes of the Fourier transform of the window function. It should be noted that due to the truncation of the ideal impulse response coefficients by the window, an oscillatory behavior can be seen in the frequency response domain of the filter, which is called the Gibbs phenomenon. As shown in figure 6.1, as the window length increases, the number of ripples in both the pass and stop bands increases, while the width of the ripples decreases. Meanwhile, the height of the highest waves remains constant regardless of the length of the window. The Gibbs effect can be significantly reduced by choosing a suitable window that doesn't change abruptly, such as a rectangular window. Now, going back to figure. It shows Gibbs phenomenon. Here you see when the length of the window is equal to 81, the transition region will be sharp, and the red plot indicates the window of size 11. Okay? Having slowed transition, but sharp transition for bigger window. Okay. In the following, we will learn about other types of window function. FIR filter design steps using window method. Choose a window function that produces the desired attenuation in the stopband as well as possibly the passband ripple. Compute or calculate the approximate number of filter coefficients n from the width of the desired transition region. Compute n sample values of the window function W of n. Find the impulse response of the ideal filter for a filter whose cutoff frequency are centered in the transition region. That's a major point. Closed solutions can be obtained for simple filters. In other cases, DFT can be used provided that enough zero padding is used. Multiply the window and impulse response values to get the filter coefficients. Usually, these values should be symmetrical to lead to a linear phase for FIR. Okay? Calculate the frequency response of the filter to check whether the desired specification is met or not. Now, taking an example. Find the coefficients of an FIR low-pass filter that satisfies the following properties using the window method. Passband edge frequency 2 kHz. Of course, we here don't care about cutoff frequency and passband frequency. They are both the same for us. For instance, transition region. Delta of F is equal to 800 Hz. Stopband attenuation 40 dB. Sampling frequency 8 kHz. Okay? So remember the parameters: 8 kHz, attenuation 40 dB, passband frequency 2 kHz, and transition region 800 Hz. Now solution. According to table 6.1, we choose H desired of n for the low pass filter, which is given as follows. H desired of n will be equal to 2 times F Cn. N stands for normalized. Okay? Cutoff frequency being normalized, FCN, times sine of n omega Cn over n omega Cn when n is not equal to 0. Otherwise, it will be equal to 2 times FCN. Now, what about table? Here you see the table. Summary of ideal impulse responses for standard frequency selective filters. Okay. Filter type. Low pass filter. Okay. Here you see what has happened. H desired of 0 to FC. And similar discussion for high pass. Okay. I will leave it for you to have a deep look. Here, for example, you see having two sink for band pass filter and band stop filter. For high pass filter is minus whatever you mention for low pass and blah blah, of course, except for HD of 0. Okay? Anyhow, we want to design a low pass filter, so we will use this information from the table 6.1. On the other hand, the width of the normalized transition region relative to the sampling frequency, of course, is equal to transition region over F of S will be 800 over 8000. We will have 0.1 as delta F being normalized. Okay? 0.1. The next table shows that Hanning, Blackman, or Kaiser windows meet the stop-band attenuation requirements, both greater than 40 dB. According to the second column of the table, it can be seen that among these three windows, the Hanning window has the smallest filter degree. So, as a result, the Hanning window is selected. For this window, we will have 3.1 over 10 is equal to delta Fn, which is equal to 0.1. So we will find the degree of the filter being equal to 31. As a result, n is equal to 31 is selected. The filter coefficients are obtained as h of n is equal to h desired of n times w of n for n greater than or equal to minus 15 up to less than or equal to 15, having 31 samples, completely symmetric. So we will have linear phase, where h desired of n is equal to 2 times fcn times sine of n omega cn over n omega cn, for n not being equal to 0, otherwise it will be 2 times fcn, and meanwhile the window will be w of n is equal to 0.5 plus 0.5 times cosine of 2 pi n over the degree 31. Due to the smearing effect of window on the filter response, the cutoff frequency of the resulting filter will be different from the given cutoff frequency in the specification. So, to compensate, the cutoff frequency must be moved to the middle of the transition region. Please remember it. Here we see the details for low-pass filter. Later you will solve other types of filters such as high-pass, band-pass, and band-stop. So, moving cutoff or passband to the middle of transition region for low-pass means FCN will be equal to FP plus delta F over 2 divided by Fs, which will lead to 0.3, showing every details. Considering that h of n is symmetric, we only need the values for h of 0 up to h of 15 to be computed. So here we have shown every details for computations. N is equal to 0 will lead to 0.6, and 1 h1 will be 0.2996. Of course it will be h of minus 1 as well, and h2 and up to h15. Okay, so we have done everything for design. But what about table 6.2? Here you see very important information. I will explain it in detail. Summary of important properties of conventional window functions. Okay? The name of the filter. Let's have a look. Rectangle, Hanning, Blackman, Kaiser. Okay? The second column. Width of transition, of course normalized. 0.9 over 10, 3.1 over n, 3.3 over n, 5.5 over n, and Kaiser is complex. I don't read that. Now, ignore about the third column, ignore about the fourth column, but start the operations from 1, 2, 3, 4, column 5. The specification had told 40 dB attenuation. Okay, the first window cannot do it because at most it will provide 21 dB attenuation. So forget about the first window. The second window, it's okay. 44 is greater than 40. We should stop here without moving further. Of course, Hamming will give 53 dB attenuation. Maybe you should be tempted. 53 is better than 44. But remember, we had been asked to have 40 dB. So you are not permitted to use such a window. And forget about 74. Why? Because it will lead, Hamming will lead to larger window, 3.1 compared to 3.3 over n is better because it will be equal to delta f. So n will be the smaller one. Here n will be bigger than what you find for Hanning. And Blackman, of course, will have lengthy window compared to these two. So, if the mentioned attenuation suffices, just stop and don't go more. Okay? Now, let's have a look to the shape of the window. Rectangle, of course, it's one for the duration of the window. Hanning has a cosine for 0.5 plus 0.5 times cosine of 2 pi n over capital N. Hamming using another strategy for using cosines. You see here 0.54 and 0.46. 0.5 plus 0.5 will be 1 for n being 0. And the same story here 0.40 54 plus 0.46 will be 1 for n 0. And the same story for Blackman. Okay. And you see here the Kaiser having another extra parameters which will be explained very soon. Now take home 6.2. Modify the parameters and design at least for 3 cases of low pass filter. Then try other types, high pass filter, band pass filter, and band stop filter. Now, Kaiser window is defined as follows. I won't read it out. You see here the form of window and definition for I0 here used. It's a Bessel function. We don't want to teach mathematics, so we will have a speed up over this discussion because normally the Kaiser is not used. Maybe in the last times it was important, but today it's not important. You will find it out why. Anyhow, having a discussion related to Kaiser, computing the degree, and information about beta. Now, important example. For a window-based low-pass filter, write a Python code for the specification as follows. Fs 8 kHz, Fp 2 kHz, delta F 800 Hz, attenuation 40 dB for stop band. Now we will run Python code. Okay. Here you see it's a low pass filter. fs over 2 4000 hertz here, and cutoff and stop band frequency has been computed and shown in figure. Okay, what we have written to find it out, we will see it inside lecture note. A definition for finding cutoff and stop band. No. The degree has been declared 31, attenuation 40, delta F 800, FC or FP 2000, FS 8000, and FFT 1024. No. FS FC plus delta F numerator has been computed using FIR win. You see here the details. We have used Hanning window. Okay. The numerator for FIR is always 1. Okay. And having some zeros to the length of num minus 1. Here we have tried to compute F and H using signal.freq z num denom, having declared n of FFT and sampling frequency. Anyhow, you saw the results as a plot. Okay. Now the next example. Write the previous Python code for a high-pass filter. Okay. Here you see, without running the program, only showing the syntax: 31, attenuation 40, delta F 800, cutoff 2000, sampling frequency 8000. Here we'll have Fs being equal to Fc minus delta F because it's high pass and the stop band is less than cutoff. Okay, so that's the only difference, and the rest is similar. Okay, again using Hanning window and similar code. Now, for a window-based bandpass filter, write a Python code for the specification as follows. I will run it. Again, 8 kHz for Fs, the first passband 2 kHz, the second 3 kHz. We have two passband frequencies. Delta F is 800 and attenuation again 40 dB. Okay, now I'll run the program. Right. Here you see two passband frequencies, FP1 and FP2, and two stop band frequencies, FS1 and FS2. And the computed results, FC computed is 2097, and the second one 2894. Fs computed 1621, and the next one 3371, and delta F computed 476 and 476. Anything. Okay. Here you see the details. Now, N31, AS40, delta F 800, FC1 2000, FC2 3000, FS 8000, and FFT 1024 fs1 will be fc1 minus delta f, fs2 will be fc2 plus delta f, again using FIR win, and window type is Hanning. And finding frequency response and plotting the results. Now, for band desktop, I won't run the program, but we'll show the style. Write a Python code for band desktop filter with the following specifications. 8 kHz, this time two stop band frequencies, 2 kHz and 3 kHz. Delta F has been kept similar to previous design, 800, and attenuation 40 dB for a stop band. Now, the major part is that this time here 2000 and 3000 are defined as stop band frequencies. Or here a typing mistake, copy and paste from the previous program. Here you see FC1 will be FS1 minus delta F, and FC2 FS2 plus delta F, and the rest is similar to previous results. Okay. Take home 6.3. Try all window types mentioned in table 6.2 and report the changes being witnessed. You shouldn't use always the Hanning. Try other one and report what you see, what happens. Okay. Study other available windows such as Bartlett window and write coding for it. Okay. We haven't mentioned Bartlett, and we have left it for self-study. Also, change the degree of the filter from lower values up to higher ones and criticize the results. Try both odd and even degrees. Write codes for plotting the shape of all windows. We didn't plot the shape of the window by itself. We just plotted the result for frequency response. Okay, I urge you to plot the shape of the window as well. Now, does the window-based FIR design yield the defined specification? Explain why. Advantages and disadvantages of the window method. An important advantage of the window method is its simplicity. It's both simple to implement and simple to understand. The window method requires minimal computational effort even for the more complex Kaiser window. The big disadvantage is the lack of flexibility. Both passband and stopband ripples are almost equal, so the designer may end up with either too little passband ripple or too much stopband attenuation. Due to the convolution effect of the window's spectrum with the desired response, the passband and stopband edge frequencies cannot be determined accurately. So, this method is under question. Again, cannot be determined exactly and accurately. Can you use it in serious designs? Okay. For a given window, except Kaiser, the maximum ripple amplitude in the filter response is constant regardless of how large n is chosen. You will have all of these answers inside the take-home I declared. So, the stopband attenuation will be constant for a window. In other words, for a desired attenuation characteristic, the designer must find a suitable window. Another disadvantage of the window method is that both passband and stopband ripples have their greatest values near the edges of the passband, especially for a rectangular window, which gradually decreases as they move away from that area. We'll show it in figure 6.2. This type of answer is not optimal. An optimal filter has ripples with a constant maximum amplitude for the passband and the stopband and are independent of each other. Here you see what we explained. Okay? Cutoff stopband frequencies. The maximum deviation happens here in the passband, and little by little it vanishes. And the maximum ripple happens here near Fs, a stopband frequency, and it vanishes. Okay? We want equi-ripple in passband and also in stopband. But this method cannot do it.